Welcome back to the deep dive. In our previous sessions, we've really dug into the technical side of ISO 26262, the concept phase, hardware, software, the V model's left side.
Right, the core development phases.
Exactly. But today, we're shifting gears a bit.
We are?
We're diving into ISO 26262 Part 8, supporting processes. Now, if those technical parts are, say, the engine of the car, then Part 8 is kind of like the robust management system around it, the thing ensuring it all runs smoothly and crucially safely. It's the infrastructure, right?
That's a great analogy. It really is the organizational spine holding everything together. Parts 1 to 7 tell you what technical goals to hit.
Right.
Part 8 tells you how to manage the whole process to actually achieve and prove those goals consistently.
So consistency, repeatability.
Repeatability, building confidence in your tools, your components, and ultimately ensuring you have that full traceability for the safety case. That's the mission here.
Okay, let's unpack this. Because supporting processes might sound a bit dry, like pure paperwork.
It can sound that way, but it's far from it. It's the regulatory backbone, really.
So where does it actually connect with the other parts? How does it touch every phase?
Oh, it's everywhere. It dictates how you handle configuration management, knowing the exact version of every single piece of code, every requirement.
Okay.
It also governs how you set up agreements between companies like OEMs and suppliers, those development interface agreements, or DIAs.
The DIAs.
Exactly. Without these Part 8 processes properly implemented, you might design safe hardware or software.
But you can't prove it.
You can't reliably prove it works under strict control, especially when things inevitably change.
Right, that makes sense. Let's start with a bedrock of any rigorous process. Documentation.
Yeah.
The standard is clear. This isn't just nice to have.
Absolutely not. It's a mandatory work product. Every single phase generates documentation that's required.
While the insistence transparency, audits.
Both. It provides transparency, allows for reproducibility, and it's the fundamental basis for any audit. And of course, it builds up the evidence for that final safety case.
What are some key documents we're talking about?
Well, you've got the overall safety plan, the HARA reports detailing the hazard analysis, the functional and technical safety requirements, the FSRs and TSRs, and naturally, all the verification plans and reports.
And keeping track of all that, that's where configuration management comes in.
Precisely. CM is what makes the documentation and ultimately the safety case valid and manageable. It turns static documents into controlled assets.
How granular does that control need to be?
Very granular. Every work product, and I mean every work product, from a requirement doc to a software module, a schematic, a test script, needs a unique ID.
A unique identifier.
Yes, and a complete version history. But the really critical part of CM is establishing baselines.
Baselines. Okay, explain that. In automotive, things move so fast, freezing seems difficult.
It can be, but it's essential. A baseline is basically a formal approved snapshot of the system, or part of it, at a specific point in time. Think requirements baseline or software release baseline.
Okay, a frozen state. Why is that so crucial?
They serve as fixed reference points. Let's say a supplier gives you a new firmware version for a chip.
Right.
If you don't have a solid agreed upon hardware baseline, you might accidentally integrate that new firmware without realizing it hasn't been tested against your current safety requirements baseline. Baselines let you roll back if needed, and they are absolutely essential for doing accurate impact analysis when changes occur.
Ah, okay. So if requirement X changes, the baseline tells you exactly which version of the design document, which software build, and which test results are linked to the old version of requirement X.
Exactly that. Traceability. And this leads to what best practices call the single source of truth.
How do teams actually achieve that? It sounds like complex tool integration.
It usually involves integrated tooling, yes. It's not enough to have requirements in Word, code in Git, and tests in Excel.
Right, disconnected systems.
The goal is to have tools requirements management, version control, test management that are linked, so an auditor or even your own team can click on a safety goal, trace it down to the specific lines of code that implement it, and then trace sideways or up to the exact test case results that verify it, all corresponding to a defined, controlled baseline.
Okay, let's talk change. It's inevitable in any project. New features, bug fixes, maybe even fixing a safety issue found late. Part 8 connects change management very tightly with configuration management, you said.
They are intrinsically linked. You can't manage change effectively without solid configuration control. Any change, especially to safety-related items, needs a formal, controlled process.
Why so strict? To prevent accidental safety issues.
Precisely. It prevents engineers from making seemingly small changes that could unknowingly introduce new hazards or break existing safety mechanisms. It forces a methodical approach.
So what does that workflow look like? The change request or CR process.
Typically, it starts with someone submitting a change request, a developer, a tester, maybe product management.
Okay.
But the absolute core of the process, the real gatekeeper, is the impact analysis.
Impact analysis. This sounds critical. Who does that, and what are they looking for?
Usually, the safety manager or a designated safety engineer leads this, and they're assessing the full impact of that proposed change. It's not just technical, it's a risk assessment.
And here's where it gets really interesting. What specifically are they evaluating? The stakes seem incredibly high if they miss something.
They're looking at potential impacts on safety, compliance, and of course, project constraints like cost and schedule. But focusing on safety and compliance, they have to ask, could this change lower the ASIL of a function? Could it reduce the effectiveness of our diagnostic checks, our diagnostic coverage?
Right. Does it mess with the safety mechanisms?
Exactly. Does it invalidate assumptions we made in our FMEA or FMEDA? They use tools like the Requirements Traceability Matrix, the RTM, to see everything downstream that might be affected, other requirements, design elements, test cases.
So, for example, changing some input validation logic.
Yes.
The impact analysis has to prove that you didn't just accidentally make your ASIL C component behave like an ASIL B one because you simplified how it detects faults.
You've got it. That's precisely the kind of detailed check required. And only after this thorough analysis is done, and believe me, for high ASIL projects, this can take significant effort, does it go to the Change Control Board, the CCB.
The CCB makes the call. Approve or reject.
Correct. And if it's approved, implemented, and then rigorously verified, including regression tests to ensure nothing else broke.
Then what?
Then, crucially, the relevant configuration baselines are updated to reflect that change. The loop is closed, and the change becomes part of the new controlled state of the system.
Okay, moving to verification. We know verification aims to find errors early, show requirements are met. It's the right side of the V model. But Part 8 adds this layer about ASIL and independence. What's that about?
Ah, yes. Independence in verification. This is fundamental in ISO 26262. The core idea is the higher the potential risk associated with a failure, the ASIL level, the more independent the verification activities need to be.
Meaning the person checking the work shouldn't be the person who did the work.
Essentially, yes, but the required degree of separation increases with ASIL. The standard doesn't trust us to grade our own homework when the stakes are high.
Okay, break that down for us. How does it scale with ASIL, especially up to ASIL D?
Sure. For ASIL A, the lowest level, basically no independence is mandated. The developer can verify their own work, although it's often still good practice to have someone else look.
Okay.
For ASIL B and C, you need what's called moderate independence. This means a different person must do the verification or review, but they can be from the same team.
Still within the same group.
Right. But for ASIL D, the highest level, you need high independence. The verifier or reviewer must be independent from the team that developed the item. Often this means someone from a separate department or even a different organization.
Wow, that sounds like a significant organizational hurdle and potentially costly. Why such a strict separation for ASIL D?
It's all about minimizing bias, particularly confirmation bias. If you design something, you inherently have assumptions and expectations about how it works.
You test what you expect to work.
Exactly. High independence brings in a fresh perspective, someone whose job is specifically to challenge the work product and ensure the verification evidence is truly objective and strong enough for, say, regulators.
Makes sense, even if it's demanding. Now let's talk about the tools we use for development and verification. Compilers, static analysis tools, maybe code generators. Part 8 has something to say about these too, right? You can't just grab any compiler off the shelf for high ASIL work.
Definitely not, because the tool itself could be faulty. Imagine a compiler silently generating incorrect machine code.
Ooh, that's bad. Hard to detect.
Extremely hard. It could directly lead to a safety goal violation. That's why Part 8 requires tool qualification for certain tools. This is governed by the tool confidence level, or TCL.
Tool confidence level. Okay, how do you figure that out?
The TCL depends on two main factors: tool impact, or TI, and tool error detection, or TD.
TI and TD.
Right. TI assesses how likely a tool malfunction is to cause a violation of a safety requirement. TD assesses how likely your existing development or verification processes are to detect an error introduced by the tool.
So high impact and low detection probability is the danger zone.
That's the highest concern, yes. We specifically worry about Tool Impact Level 3, TI3. These are tools whose malfunction could directly introduce errors that violate safety requirements, and these errors are difficult to detect through normal testing, meaning low TD.
Like a compiler or a model-based code generator.
Exactly. If your tool falls into that TI3 category, qualification becomes mandatory. You have to actively demonstrate that you can trust this tool.
And how do you do that? What are the qualification methods?
The standard provides a few options. You could show increased confidence from use, basically, providing extensive evidence that the tool has been used successfully in similar contexts for a long time.
Okay, historical data.
Or you could evaluate the development process of the tool itself. Did the tool vendor follow rigorous standards? Another way is to systematically validate the output of the tool. Or, in some cases, the tool itself might have been developed according to ISO 26262.
Part 8 also offers a way to reuse things, which sounds practical. If a team wants to use hardware or software that already exists, maybe a CO test component, there's this proven in use argument.
Yes, the proven in use argument. It's a way to potentially avoid doing a full ISO 26262 development cycle from scratch for a component if you can sufficiently demonstrate its safety based on prior field experience.
Sounds useful. What kind of evidence do you need?
Well, the standard is quite specific. You need solid evidence of usage history in a similar application and environment. You need sufficient operational hours or mileage showing a demonstrably low failure rate in the field.
Low failure rate.
And importantly, you need records showing that any failures that did occur were properly analyzed and that effective corrective actions were taken. It's not just about showing it worked, it's about showing you managed its issues responsibly.
What are the limitations? Say I used a component in a previous car model that was maybe only QM or ASIL-A. Can I argue proven in use to put it into a new ASIL-C system?
You could try, but it would be very difficult. The argument typically isn't considered valid if the new context is significantly different.
Like a higher ASIL.
Exactly. A higher ASIL requirement, a harsher operating environment, maybe higher temperatures or more vibration, or even just a different usage profile. The historical data has to convincingly support its suitability for the new, more demanding application.
Got it. So reuse requires strong justification. This brings us towards the pointy end.
Yeah.
The safety analyses needed to quantify safety. Part 8 mentions several techniques. Can you quickly differentiate the main ones? FMEA, FMEDA, FTA?
Sure. First, FMEA failure modes and effects analysis. This is a bottom-up method. You look at individual components, brainstorm how they could fail, the failure modes, figure out the consequences, the effects, and then typically rank them using a risk priority number or RPN.
Okay, bottom-up, qualitative focus.
Mostly qualitative, yes. Then you have FMEDA failure modes, effects, and diagnostic analysis. This builds on FMEA but adds quantitative aspects. It uses actual component failure rate data, often in FETHT's failures in time,
FA traits,
to calculate metrics like diagnostic coverage, DC, how well your safety mechanisms detect faults, and the safe failure fraction, SFF, which relates to the proportion of safe or detected faults.
So FMED is quantitative FMEA, basically.
In essence, yes. And then there's FTA fault tree analysis. This one is top-down.
Top-down.
You start with an undesirable top-level event like unintended acceleration, and you use logic gates and gates to break it down deductively into the lower-level component failures or events that could cause it. It helps identify critical failure combinations.
Right. And these analyses, particularly the FMEDA, feed into those critical hardware safety metrics we hear about for high ASILs, SPFM and LFM.
Precisely. These metrics are derived from the FMEDA results and are key requirements for demonstrating sufficient hardware safety against random failures.
What exactly are they measuring? Let's start with SPFM.
SPFM is the single-point fault metric. It quantifies how well your system handles failures that could immediately violate a safety goal if they occurred on their own single-point faults. It measures the percentage of these faults that are either inherently safe or are detected controlled by a safety mechanism.
And the target for ASIL-D is high.
Extremely high. For ASIL-D, SPFM must be greater than or equal to 99%. You need to catch almost all critical single failures.
Okay, 99%. And LFM, latent fault metric.
LFM targets a different kind of failure. Latent faults are hidden faults, faults that don't immediately cause a problem but might disable a safety mechanism without anyone knowing.
Like a backup system failing silently.
Exactly. LFM measures the percentage of multiple point faults, typically a latent fault, combined with a second fault that reveals it, or causes the hazard that are detected or perceived by the driver. It's about ensuring your safety mechanisms themselves don't silently fail.
And the ASIL-D target for LFM?
It's also demanding, greater than or equal to 90% for ASIL-D. Achieving high SPFM and LFM requires very robust diagnostic capabilities designed into the hardware.
One last major area in Part 8. Modern cars are complex systems, often built with components from many different suppliers working with the main manufacturer, the OEM. How does Part 8 manage the safety responsibilities across these organizational boundaries?
Through the Development Interface Agreement, the DIA we mentioned earlier, think of the DIA as the formal contract or agreement between two parties, usually the customer, like an OEM, and the supplier, like a Tier 1, laying out exactly how they will collaborate on safety-related activities.
What absolutely needs to be defined in that DIA to make it effective? What needs to be rock solid?
Several things are crucial. First, a clear allocation of all safety activities and responsibilities. Who is doing the HARA? Who develops which safety requirements? Who performs the verification for specific components? Who writes the safety manual?
Defining roles and responsibilities clearly.
Unambiguously. It also needs to define the specific work products that will be exchanged between the parties, the formats, the review, and approval processes for those exchanges.
And what happens if things go wrong? Disagreements.
That too. A robust DIA defines the joint procedures, including communication channels and, very importantly, an escalation mechanism for handling disagreements or safety issues that arise during the collaboration.
And does the traceability we talked about earlier need to cross this boundary too?
Absolutely critical. The traceability chain must be maintained seamlessly across the interface. If the OEM allocates certain safety requirements to the supplier, the supplier's implementation and verification evidence for those requirements must trace back clearly, often through a shared or linked requirements traceability matrix, RTM, to the OEM's original safety goals. The final safety case presented by the OEM relies on this unbroken chain. Hashtag tag outro.
So, wrapping this up, we started by calling Part 8 supporting processes. But listening to all this, it's really the core governance layer, isn't it? It's what gives functional safety its teeth.
I think that's right. It elevates functional safety from just clever engineering design to a mature, managed, and auditable discipline.
It forces that organizational maturity.
Exactly. Without the rigorous framework, Part 8 provides the configuration management, the change control, the demands for verification independence, tool qualification. The DIA's, even the best technical solution, lacks the necessary proof, the required confidence, to be deemed safe enough for our roads.
So maybe the hardest part of getting to ASIL C or D isn't always the initial invention of the safety mechanism.
Often.
But rather maintaining that auditable proof through these Part 8 processes that your solution consistently works as intended, no matter how many times requirements change or software gets updated over the vehicle's lifecycle.
That's a huge part of the challenge, absolutely. Consistency and evidence. Which
leads to a final thought for you, our listeners. Think about the processes you use in your own work environment, whatever field you're in. If you had to face an ISO 26262 Part 8 style audit tomorrow, focusing on change control, configuration management, and traceability, which of your current practices might not make the cut? Something to ponder.